Hello and welcome to a special coding challenge. This is a special coding challenge that I'm doing actually to celebrate, in some ways, 200,000 subscribers. And I also want to do this as a bonus coding challenge in solidarity and support of refugees and immigrants. I'm not interested in any walls, and I'm interested in welcoming. And so to celebrate 200,000 subscribers, I'm donating $200 to each of these worthy organizations that will be linked in this video's description. And if watch this video and enjoy it, if you feel inclined to donate, that's great too. But I'm happy to do this video in support of these wonderful organizations. Okay, now what's in this video? This is an example of an Islamic tiling pattern. This is from the Bibi Kanu Mosque in Uzbekistan. It was completed in 1404. And what's amazing about these kind of patterns, if I zoom into it, let me zoom. It's actually a higher resolution image, is you can see this amazing algorithmic tiling geometry. It is beautiful, and what's amazing about this kind of stuff that you can find, and there are countless examples of this in many cultures for many thousands of years, these algorithmic geometric tiling patterns that we work out code or mathematical formulas from, people have thought about and done very carefully by hand. So in art and architecture throughout history. So I would love for you to share in the comments your favorite historical geometric tiling pattern, and I'll maybe come back and do future coding challenges. There's a great book called Symmetry. I don't have my prop here. Someone can like Photoshop in that book. I have it downstairs. Linked about this book in this video's description, which also has lots of wonderful examples. So in this challenge, I'm going to try to implement an algorithm that, that generates a styling pattern like this. So the algorithm that I'm going to take a look at comes from this particular paper. You can see here, look at these geometric possibilities. In a minute, when I start the coding challenge, I'll show you more about this paper. And in the end, what I'm going to have is something that looks like this. So I'm actually recording this after I finish the challenge. So you can see this is me first being able to sort of generate and create different patterns that approach this idea of these star patterns with some different parameters. So a couple things to mention. This is a particularly long video. This is a complex topic. There's lots of things that I skirted over that I should probably make some separate videos about. I also, at the end, finished the video and then thought of and fixed a bunch of bugs afterwards, like 2 or 3 times. So if you really are interested, watch all the way to the end. There'll be a couple addendums. And then what I'm asking you to do is share in the comments share in the comments other interesting tiling patterns that are beautiful to you, that might be worth investigating in future coding challenges, and also check out the GitHub repository that'll have a link to this particular example running online, and I would love for people to contribute to it, and we'll make it a bit more sophisticated. And when I come back for my regular live stream this Friday, I will follow up and show you hopefully some more exciting and interesting examples of colors and patterns with this particular algorithm, okay? So thanks for tuning in to this coding challenge on the coding train, and see you at the end of this video. Okay, I am ready now to work on this coding challenge. And this coding challenge is based on Islamic star patterns from Polygons in Contact, a paper from the School of Computer Science, Craig Kaplan, University of Waterloo. And I'm not going to, as much as I would like to just do a dramatic reading of this paper, I'm mostly just going to follow the diagrams in terms of this challenge and try to work on coding stuff out. And those of you I encourage to read the paper and point out everything I did wrong in this particular video. So I'm going to refer to it when necessary, but this is the main component here of how this is going to work. And I'm going to start with a diagram. So this is a diagram here, but I need to draw this myself in order to understand how this works. So the way that this algorithm works is if you have some regular tiling of polygons, and you can get very complex and sophisticated with this, I'm going to build a really simple example. My tiling will just be a grid. So I want to have in my canvas a grid of squares. And then if I pull out one of these squares, what do I do? Any polygon has a certain number of sides. For each and every side, I want to find the midpoint. This is the midpoint. Then what I want to do is send out a ray, a vector, an arrow from that midpoint, and based on some angle of rotation from the side. So the angle that I'm going to use to start with will be 60 degrees. So if I send these out, oh, this is like a bad way that I've drawn this, because it's going to work out so too perfectly. So, and then as these go out, the ray that they intersect with first most closely, they stop. So this actually, weirdly enough, the way that I drew it created a square, but let me make it different. So what if I do this? You could imagine seeing something like this. Boy, my drawing skills are terrible. But you can see here I'm starting to get a star pattern. So based on that angle, I get a star pattern. And incidentally, if this is tiled next to another polygon, this is going to go out this way. And if I make my polygons something more interesting, like a hexagon with maybe, a couple smaller hexagons, I could come up with some clever, or some triangles. You could imagine that this is also going to give me even more interesting patterns. And the idea here is that then, once I do that, let me get my eraser. Once I do that, I erase that original grid, and I'm left with these star patterns. So this is the idea of recreating one possible algorithm to recreate this style of star patterns based on a grid of polygons that are in contact with each other. So that's what I'm going to try to build. So coming back over here, the first thing that I want to do, and you can see this, there's an important aspect of this that I didn't explain, which is that, notice the way that I drew it, these rays are going to come out from the same point in the midpoint of the side of a polygon, but the paper talks about a value called delta. If I separate those rays by a little bit, then I get further, I'm further playing with the pattern and making it more beautiful and interesting and star-like in ways. So I'm going to also need to introduce this delta as well. Okay? So here we go. So one thing I should mention is from this paper is a discussion of a system called Hankins method. And Hankins method, I'm going to just click on this footnote here into the paper and take a look at it, is another reference here called The Drawing of Geometric Patterns in Saracenic Art, volume 15 of the Memoirs of the Archaeological Society of India by E.H. Hankin. So I'm just noticing this now. I would love to dig up a copy of this and read this as well. So this paper is also based on, yet again, something else. So this is called Hankins method, and the reason why I thought of that is because I'm going to need to have a few different objects. So one thing I definitely want is to have a polygon object. A polygon object describes this entire polygon. Then maybe I also might like to have an edge object. An edge describes an individual edge of the polygon. 1, 2, 3, 4. And then I might could be useful to create what I'm going to call an object called a Hankin. And I hope I'm pronouncing it. It could be Hankin. Which is just these object to keep track of these rays that I'm going to cast out from the sides of the polygon. Okay, so that's going to be how I'm going to organize the program. At least how am I thinking of it now. So I'm going to create a polygon object, and the polygon object is just going to have an array of edges. So I also need to have an edge object, and I'm going to have every edge has is a line. I'm going to keep track of the endpoints of that edge, and I'm going to call them A and B. So perhaps what I'll do is, and I guess I'm going to make these all variables that are public and available outside to view in the object. So I'm going to say this.show equals function. And actually, what I'm going to do, eventually at some point I want to do something different so I can fill these with color, but just for simplicity's sake, I'm going to loop through all the edges. And say edges index I dot show. So an edge will also have a function called show. So to show a polygon, I just say, hey, draw all the edges. And to show an edge, I say stroke 255, line from this dot A x, this dot A y, to this dot B x, and this dot B y. So I'm starting by making this idea of polygons and edges. And eventually I'm going to put these into separate JavaScript files as the code starts getting bigger and bigger and bigger. But just to start right now. And then maybe what I will do is I'm going to create a function called add vertex. So what I'm going to do is for add vertex, I am going to add an x and a y. And then I want to create point called A, which is a vector at that x and y. And then, you know what? It wouldn't hurt. I don't know if I need these, but it wouldn't hurt to have an array that also just keeps track of all the vertices. I might not need that later, but right now I'm going to just do a lot of stuff that's redundant just to kind of figure this out. So what I'm going to do is I'm going to say this.vertices.push that vector. So the first thing I want to do is when I want to add a vertex to my polygon, I want to give it an x, y where it is, make a vector out of it, and add it to this array, this list of vertices. Then, as long as, and let me do this first, as long as there's already at least one other vertex in the, as long as there's one other vertex at least in the list already, I can make an edge. And you know what I should do? The way that I make an edge, oh yeah, that's how I did it. Okay, the way that I make an edge is I would say previous equals this dot vertices, and you know, let me put that in a variable. So how total is this dot vertices dot length. So I now have, how many vertices do I have so far? As long as there's at least one other vertex, previous is index total minus 1. So you can see I want to look at the previous vertex. And then what I want to do is I want to make an edge, which is between what? The previous and the new one. So then I add, and then I can add this dot edges push edge. So I'm kind of writing a lot of code without even running. Let's just see if I have any errors. Refresh. Okay, so I have some errors. Sketch.js line 11. This equals function. And there we go. So now look at this. What I have so far is this idea of a polygon object. So I have a polygon object, which is a generic polygon. Could be a square, a trapezoid, a hexagon, a heptagon. And what I want to do, by the way, hyperbolic heptagonal tiling. That's a cool thing. Look that up. So I can add vertices. Have an x, have a y, have an x, have a y, have an xy, have an xy. I can add them, and it'll create edges, and then I can display it by saying edges.show. And an edge is just a really simple thing. It's 2 points, and I can display it as a line between those 2 points. So let's try making one polygon, a simple one. Okay? So I'm going to create a variable, poly equals, called poly. And I'm going to say poly equals a new polygon. And then I'm just going to add some vertices to it. Add vertex 100, 100. Add vertex 200, 100. Whoops. Add vertex 200, 200. Add vertex 100, 200, and then poly.show. Ready? Let's just see. So if I did all my code correctly, I should see just a square on the screen. Okay. Poly.error edges is not defined. Oh, everybody knows. Oh, just everybody sing along with me now. This dot, this dot, this dot, this dot song. I'm sure that's what it is. What line was that? Line 32. Yep. This dot edges dot length. This dot edges dot show. I'm sure I'm missing more. X is not defined at sketch.js line 45. Oh, interestingly enough. Okay, hold on. No, so you know what? To debug this, I feel like now I already need separate JavaScript files because I'm doing that horrible scrolling thing. So I'm going to create a JavaScript file called polygon.js, and I'm going to take my Polygon constructor function, and I'm going to put that in here. Then I'm going to create a file, and I'm going to call, no search. I'm going to create a file, and I'm going to call it edge.js. And I'm going to go to Sketch, and I'm just going to take, that has very little code in it. But this is going to make life a lot easier to try to figure this out. So, of course, I need to also make sure I reference edge.js and Polygon. Polygon.js, now that I have added those. Okay, edge, edge, edge. So that's working. And then edge.js line 7. Oh, I have an extra this.b in there. Oh, my goodness. Lost my mind. Thank you. There we go. We've got our square. But now, the thing is, where's that last edge? I need to get that last edge. So what I'm going to do, if we look at the polygon, is I really should connect the first one with the last one. I'm going to write a function called close that I can just call that just says var edge equals a new, let me get the last one. There's probably a JavaScript function that will, like I can do like pop or something like that, or shift that just gives me the last one of the array. But here I could just grab the last one, and then I can say the first one, this dot vertices 0, and I can make a new edge from, and now wait a second, I'm going from previous, if I am thinking about this one square, I connected previous to here, then I connected here to here, then I connected here to here. So I want the last connecting to the first. And so what I'm going to do that is I'm going to say I want the new edge, the last connecting to the first. And now edges.push edge. And then what I just need to make sure I do is in the main sketch, when I'm finished, I'm going to call that close function. So in my Polygon object, and by the way, I'm sure there are some great geometry library that we could just use that would do all this for us. So I look forward to your fork of this that makes it much nicer with a sophisticated geometry library. We should see, edges is not defined because, as you can all say with me, this dot, this dot, this dot, this dot's on. Okay, great. What is this? 10 minutes and I got a square on the screen? Boy, aren't I really such a exciting and interesting and engaging coder to watch. Okay, so now what do we want to do as the next step? The next step that I think would make sense is for me to start making these, what I'm going to call the Hankin or the Hankin objects. So the first thing I need to do is figure out how to find the midpoint for each side of the polygon. And again, I'm using just a square to do it in a simple way, but however I program it, I want it to be generic that it would work as soon as I change the square into, say, a hexagon or some other type of polygon. So let's first look at those midpoints. So what I'm going to do now, I think, is in the edge object, I'm going to write a function called this.Hankin. Hankin. And in this function, the first thing that I'm going to do is find a midpoint. And the way I'm going to find the midpoint is I'm going to add this dot A and this dot B together. And then I'm going to say mid dot multiply 0.5. So this is a function in the P5 library that takes two vectors and adds them together. And then multiplying by 0.5 is dividing by 2 because the midpoint is essentially the average of the 2 points. So that's going to give me the midpoint instantly. Excellent. Now, here's the thing. I want to, the other thing that I need, so what is a Hankin? What is a Hankin? A Hankin. Okay, so here's the thing. I want to keep track of array, essentially. So I need a starting point, and I need a vector that's pointing in a given direction. So that's what I want a Hankin to be. So I'm going to come back over here. I'm going to make a new JavaScript file, because I'm overdoing my objects here. And I'm going to call it hankin.js, and function Hankin. And I know a Hankin should have a starting point, which I'm going to call A, and a V, which is the vector of the direction it's pointing. So this dot A equals A, this dot V equals V. So this is ultimately what I want to create. So in the edge, I know I want a midpoint, and now I need an array that points in a certain direction. Okay, so if we look at this diagram, what I want from this midpoint is a vector, two vectors, one going out this way, one going out this way. So if I could just get a vector that points from here to each of the endpoints of the edge, then all I need to do is rotate it by some angle, and I have the two Hankins. Okay, so let's try to do that. So what I need is the midpoint and the edge points. But look at this. I have the edge points are A and B. The midpoint is I just calculated. So I should be able to say now, var v1 equals p5.vector subtract this dot a, the midpoint. So this creates a new vector. And by the way, a lot of this could probably be optimized with creating fewer vector objects and reusing them, but I'm kind of not going to worry about that right now. I could always come back and optimize and clean this up and make it more efficient later. So I want to say, give me a vector. The way I get a vector pointing from one location, A, to B, is I just say B minus A, and then I've got a vector pointing there. So that's one, V1. And then V2 is pointing from the midpoint out to B. So now, I've got a Hankin for some Hankin, I guess. I don't know, never mind. I stole that joke from the chat, by the way. Not that that's a joke. Not that that's funny, I guess. Apparently I make dad jokes. Is that what it's called? Cringe is now being typed into the chat. So I am going to now say var h1 equals, and actually what I'm going to do is I'm actually going to give the edge a reference to two Hankins. And I'm going to say this dot h1 equals a new Hankin from A with a direction of v1. This dot h2 is a new Hankin, B to v2. Okay. I think this is good. So now, why not when I call show, let's just say this dot h1 dot show, this dot h2 dot show. So when I show the side, the edge, I'm also going to show the Hankins that are emanating from the midpoint of that edge. And the Hankin function then needs a show function. And there's a lot more that I need to add to this. But just for right now, what I'm going to do right now is I'm going to say this dot b equals p5 vector add a comma v. So what I want, right, remember what I have is I just have, can you see this over here? I just have a point A, and then I have a vector v. But what I want to do to be able to display this just for debugging is I want to have a point A and a point B that I can just draw a line between. So if I take A and add v to it, now I have point B. And actually what I'm going to need to do is, this is actually a little bit of a problem because it's I know it's fine because the Hankin vector has an arbitrary length. I'm going to need to normalize that vector and make it length 1, but we're getting there. This is just for debugging. I'm now going to say stroke 255, line, this dot A dot X, this dot A dot Y, this dot B dot X, this dot B dot Y. So that should also draw a line. So here we go. Now in the sketch, I add vertices. And I close it, and then I should probably say I need to calculate all the Hankins. So I have a lot of function called Hankins here. I'm going to say poly.Hankin. So I need to add a function to the polygon, which all it does is it loops through all of the edges, which I already have a loop, and has each edge call the function Hankin to calculate its Hankins. So basically, right, I have almost this hierarchy. The polygon is the overall shape. The polygon keeps track of a list of edges. And then each edge keeps track of its starting point and end point and the two rays emanating from it. So what I'm doing is saying, hey, polygon keeps track of the edges. Hey, all you edges, calculate your Hankins, so to speak. So now if I refresh this, Hankin is not defined. Import, I forgot the import. Everybody was reminding me in the chat. And yet I forgot it anyway. So I need to add Hankin.js. I'm going to hit refresh. Interesting. One thing that I want, let's just do something for a second, which is let's rotate it by each one by 60 degrees. And, yeah. And just to see, I just want to see something for a second. Let's rotate by 60 degrees. And while I'm doing that, I want to work in degrees just for, and so I'm going to say angle mode rather than radians. Natively, JavaScript, P5, et cetera, is going to think in terms of radians, but I can adjust that by using angle mode degrees. Yeah, okay. This is actually a bit more like, so something is way off, but we'll fix it. I'm not worried. Oh, this should be mid. This should be mid. What was I doing? these need to be the midpoint. The whole point of this was to draw them emanating from the midpoint. There's the problem. Okay. I don't know if I need to. Okay, so here we go. There we go. So now you can see they are emanating from the midpoint. Now this is right, but they are rotated in a very particularly strange way. So let's take out the rotation for a second. Is it really doing it by, let's just double check. Okay, who knows? Maybe angle mode degrees and radians is broken. So let's do the conversion ourselves just to be sure. Yeah, that was the problem. Angle mode degrees doesn't seem to work properly in P5 with the vector rotation function. So I'm going to have to investigate that. It's probably a bug, although I could have done something wrong. So I need to investigate that and submit it. I actually think that I implemented this part of P5, so if it's a bug, it's because I did it incorrectly. Because I implemented a lot of the vector stuff a long time ago, I think. Anyway, so now let's rotate V2 by this. Oops, and I'm missing parentheses. There we go. So this is perfect. So look at this. We're already kind of golden. What we have now is the Hankin objects, and they are emanating from the midpoints at 60 degrees. And we can see that what I would like to do right now is just make this a variable. I'm going to say angle equals 60. And then in the edge object, I want to rotate by negative angle and positive angle. Whoops. Negative angle and positive angle. And what I'm going to do, hit refresh, same thing. Now we should be able to do things like, okay, let's make it 30 degrees, and we can see it looks like this. Make it 90 degrees, and I get that. So everything is working as expected, and I'm going to stick with 60 degrees. Now here is the thing. What we actually need to do is find this point. Am I pointing at it? I'm pointing at it. We need to find that point of intersection. And while it's quite simple to look at this and just say, well, this one always intersects with that one, and this one always intersects with that one. We could kind of know it's not going to be so simple if I start to vary this delta value I referred to earlier, or vary the way the polygon. So I need a generic way of doing this. And the way that I'm going to do that generic way is I am going to, for every one of these rays, let's do this as a diagram. What I want to do is I am going to, here is the square, and I have this midpoint, and I have this pointing out of it. And let me make it point a bit more towards the center. So what I want to do is I'm going to ignore its friend over here, its partner that's rotating the other direction. I don't care about it ever intersecting with that one, because it's never going to. When they cross, they might, but I don't want it. And now what I want to do is I want to look at every single one. So two lines always have an intersection point, unless they're parallel. So what I want to do is shoot this ray out, shoot this ray out. I can shoot this one, I can shoot this one, I can shoot this one, and I can shoot this one. So what I want to do is I find all these intersection points. And I think the way to find the correct one, right? If I just say, where does this ray intersect with all these other rays? If I find the correct one is the one that minimizes the total distance of these two. So in other words, even though it intersects with this one first, if I add up these two values, it's going to be bigger than adding up these two values. I think this is the way to do it. So what I need, by the way, is a formula to calculate the point of intersection between two lines. And thankfully, I have a website. I knew that I would need this. I have a website loaded already. I will link to this in the video's description. paulbork.net/geometry/point-line-plane. Paul Bork's site has tons of geometry formulas, and I would like to do a separate video to maybe kind of derive this. But what I'm looking for here is the intersection point of two line segments in two dimensions. And so this is actually what I need to do right here. If I have P1, P2, P4, P5, P1 being X1, Y1, P2 being X2, Y2, P2. I can use this formula to calculate these two particular values, and then I can find the X and Y intersection point with these two formulas. Okay, so what do I want to do? The edge object keeps track of two Hankin objects. So this is creating the Hankins, and then I'm going to write this dot finalize Hankin, or like I just call it find end is a function. So find ends. And what I need to do is I need to look. Here what I need to do is look for every single, okay, so what I need is all of the other edges. So I need to receive, this function needs to receive all the other edges. And I need to say for var I equals 0, I is less than edges.length, I plus plus. So first thing first is, I only want to do this if this object is not equal to, you know what I would rather do here for a second? Let's make this simpler. I'm going to make this function just receive one edge. We'll deal with this later. Right? So what I want to do is I want to find this, where does this particular Hankin intersect another one? Edge.h1. Or where does it intersect edge.h2? And then the same as, I need to test all of these. And h2. So there's a lot of tests going on here. H1 and h2 of this object needs to check the other objects h1 and h2. So actually, I think what I'm going to do, I'm going to say this dot h1 find end edge dot, I'm going to just pass this off to the Hankin object. This hierarchy thing is a little bit out of control, but I think it actually makes kind of sense. So then I want h2 to check both of these. So for this function, right, again, the polygon is going to say, every edge has a bunch of Hankin objects. For every Hankin, send to the edge the other Hankins. And then the edge is going to say, hey, you Hankins, work it out amongst yourself. So I'm kind of peeling this back. So now what I need is in the Hankin object, I need a function called this.findEnd equals function to some other Hankin. So what I need to do, this is now where I need to do line intersection. Where do those lines intersect? So that's where I need this equation here. Now, interestingly enough, look at this. Let's think about this for a second. I'm going to need to diagram this. Okay, so let's say I have x1, y1, and I have x2, y2. And then I have x3, y3, and I have x4, y4. These are the 4 points. What I really have in my program is x1, y1, and a vector that points to here. What I really have in my program is x3, y3, and a vector that points to here. So anytime I see in this particular thing, anytime I see x4 minus x3, and I have to thank MeIamSum on Twitter, who helped me with this suggestion as I was trying to work some of this stuff out earlier today. X4 minus x3 is actually that x value of that vector. I don't actually need to calculate x4 minus x3 because that's the x component of that vector I have already. So there's a lot of ways I can actually reduce that formula and make it a little bit simpler. So let's see, I'm sure I'm going to get this wrong, but hopefully those of you watching in the chat are going to be able to help me correct this. So let's see if I can now translate this formula. So what I have, what do I have? I have this dot A. I want to look for, I have this dot A and this dot V. Is that what I have? Yes. And then I have this dot, other dot A and other dot B. This is the equivalent of x1, this is the equivalent of 0.1 and then 0.2 minus 0.1. And then 0.3 and then 0.4 minus 0.3, I think. So the first thing I need, one thing you'll notice about this formula is the denominator here on both of these equations is exactly the same. So let me compute that as one thing. Equals y4 minus y3, oh, this is so hard, is, other dot v. Is y4 minus y3 is other dot v, x4 dot x. No, but it's y. Is other dot v dot y. So I need that times an x2 minus x1 is this dot vx, right? Minus, I think this is right, help me along here, minus x4 minus x3, which is other dot v dot x. Is that right? Oh my God, this is so hard. Times, now I have y2 minus y1, which p2 minus y1 is this dot v dot y. How did I do there? Did you guys think I got this right? Now the numerator, I'm going to say var, what's this 2 down here for? That's just like an extra thing. Okay, the numerator is var ua equals, let's just say numerator a equals x4 minus x3, which is, basically we're calculating like the, anyway. x4 minus x3 is other dot v dot x times, now this no longer, y1, y3, these are actual points that I need to calculate. Here's the good news. Guess what? Here's the good news. So remember this goofy b? I actually also have, if I need it, this point over here, and I have this point over here, because that's what b is. I bothered to say, hey, this point a plus the vector, give me b. So I actually have the equivalent of x4, y4, and x2, y2. I have these in b. So b is x4, y4, and b is x2, y2. Hope I'm doing this right. Hard to keep track of. Okay, now, coming back over here, this is the hardest part of the whole thing, I think. Where am I? So b, so now I need to say, y1, this, y1 is a though. So y1 is this dot a dot x minus y3 is this, no, but that's a y. Y minus this dot y, sorry, this dot, oh no, other dot a dot y. So 1 and 3 are a and other. 2 and 4, 1 and 3 are this dot a and other dot a. 2 and 4 are this dot b and other dot b. And then minus y4 minus y3, that's other dot v dot, this is something that would be really good for me to just do in advance. Other dot v dot y. Oh my God, I'm losing my mind. And the other thing is I have like no space here. I got to just make this wider. Okay, other dot v, and then I need to look at this. Where am I here? I'm on the numerator here. So I just did x4 minus x3, y1 minus y3. Now I'm doing y4 minus y3. There's a pattern here. It would be better if I just studied this pattern. Times, and then what I need here is x1 minus x3. So what did I say x1 is? Guess what? It's exactly this. This dot a dot x, other dot a dot x. Okay, how's that for the numerator a? Let's look at numerator b. This is so much fun. How many viewers have I lost? Okay, now numerator b, one thing we should notice is these are the same. So that I can copy. It's just x2 minus x1 and y2 minus y1, which I want to change. Okay, so numerator b is actually the same, except x2 minus x1 is this dot v dot x, and y2 minus 1 is this dot v dot y. So I think I got this. There's a very, very high probability that there's a mistake there. I will be shocked if there's no mistake there. But let's start with this. Now, we're going to do the easier part now. If I got that correct, var ua equals num a, numerator a divided by the denominator. ub equals numerator b divided by the denominator. It's a little bit misleading that I'm using a and b here because this a and b have nothing to do with that other a and b, but so it is. Okay, and then what I need to do is the intersection point, var x equals, and I can reduce my space now. The intersection point is, what's x1? Somebody help me out. X1 is this dot a dot x plus ua times x2 minus x1, which is this dot v dot x. And then var y is this dot a dot y plus ua, notice ua times this dot, this, I don't know why I'm putting the parentheses in weird places. The order of operations should make it work, but just to be, this dot v dot y. Oh, there's a really big point here though that I want to make. Look at all this time we spent calculating num b, the numerator b, and yet it's used nowhere in the formula at the end to get this x and y. Why is that? Well, here's the thing. There's a lot more to this algorithm than meets the eye, so to speak. Because let's just say, for the sake of argument, that these are my lines. Oops. So these lines have a point of intersection if you extend them out infinitely in both directions. So this algorithm will actually calculate this point. But that's not valid for me. I only want points that exist where I don't go backwards from the ray, only forwards from the ray. And actually, what's really wonderful about this is these UA and UB values will be negative if it's behind that ray, or positive if it's in front of. So one of the things I can do is I can actually say, this is only a valid endpoint if UA is greater than 0 and UB is greater than 0. So I can actually use this as a test. I don't even need to calculate just to know if two lines intersect each other. Okay, so what I want to do is I'm going to say this dot end equals create vector at xy. Because if I am searching to find the endpoint, I want to find where it intersects the vector, the other Hankin thing that's coming in. Now, I'm going to have to test which one's the right one, but this should give us something. So one thing I need to do now is I'm going to add this idea of an endpoint. And I don't actually need to add this up here, but I'm just doing this to keep track of things. And here I'm also going to say, if this dot end, I want to draw that endpoint just to sort of see where that is as well. So n.x, n.y. Let's make these just 4 pixels, and let's make this one like kind of a nice, some bright color so we can see it. While I'm debugging, it would be much nicer to see this. This is just like a hard-coded polygon, but whoops. Let's just make it bigger so I actually have more to see. Okay, so now what I want to see is finding some intersection points. So what I'm going to do now is I'm just going to say in the Hankin function, after I calculate all the Hankins, I'm just going to say this dot edges index 0, find ends, this dot edges index 1. So I'm just going to test this function. I'm just going to say, hey, edge 0, which should be the top one, and edge 1, which should be on the one on the right. Just see if you can find the intersection points. So this should trigger this, which should then trigger 0 checking the other ones, h1 and h2, and we'll see if we find some endpoints. And then what I want to do is see what happens. So let's refresh this. Error. Oops, there's just an extra parentheses there for no reason. There we go. Okay, so this is a good, sort of a good sign in that this, you can see, if I zoom in here, this makes sense, right? This point here is where this ray would intersect with that one. It's the wrong one. I want that one to intersect, and I want this one to intersect over here, but we're getting kind of the idea. So, and then what's the other one I found? That's really weird. What is that intersecting with? Ah, you know what? It's intersecting with this one. So this is actually correct. So if you extend this out, right, I'm just testing to see if I'm finding intersection points between lines. Now I need these Hankin objects to actually optimize to the one that it finds first. So what I need to do here is in the Hankin object, what I want to say is if it finds an endpoint. Okay, so really what this is, where is this? This is not the endpoint yet. This is what I'm going to call a candidate. And what I want to do is I want to calculate the total distance of those candidates. So let's just think of just this one, okay? And eventually what I'm going to do is test its point of intersection with all of these. So I already had this diagram earlier, so I'm doing it again. It's going to intersect with this here. It's going to intersect with this here. It's going to intersect with this here, and this one, in theory, it's going to intersect all the way down here. This one's going to get ignored because it's not actually meeting this ray. So this will get ignored because I'll get a negative UA or UB. So I really just to know, is it this one, or is it this one? And I think a way for me to do this, one thing that's interesting is it's going to be equidistant here. So I could just test if these rays are equidistant or it won't be equidistant. That's an interesting possibility. I don't know if that's always going to be the case. I think it's perfectly symmetrical, though. I'm trying to imagine if the polygon, though, is a weird shape. But I think I can also optimize for the minimum distance. So let's try kind of both of those. So here's the thing. If there is no end yet, then the candidate by definition is the end. So if n doesn't exist, then there we go. And now this should find the first one. So if I refresh this, you can see it finds the first one, right? This is working quite well. It's intersecting here, and then this one intersecting here. I'm not checking the other ones. So that's a good sign. If there is no, so now it's finding the first one. Now let's say it finds more than one. Let's say if end exists, however, if end exists, one of the things that I need to do is I need to calculate those distances. So what I want to do is say var d1 equals p5 vector distance from candidate to what? This dot a. So remember I have a and other. So I have this and other, and I want to get the distance from the new point. So if I come over here, right, and this is the point I'm finding, this is this, and this one is other. I want to get this distance and this distance. And now I want distance 2, and I can probably move this a bit over here. Distance 2 is between candidate and other dot A. And the total distance equals d1 plus d2. So if there wasn't an end, then this dot end equals candidate. And guess what? I want to keep track of the previous distance. So I'm going to make that previous d another variable. And by definition, then, this is the one I found before. This dot previous distance equals that distance. So if I haven't found an endpoint yet, that one's the endpoint, that's the previous distance. Otherwise, if d is less than the previous distance, then the previous distance is d, and I now have a new candidate, a new endpoint. So this is me. I'm going to check every single possibility and find the one that's optimal. Okay? I think this is pretty good. And now I'm going to hit refresh. And I've got the same exact answer here. But why do I have the same exact answer? Because I'm not actually checking everything against everything. I'm just checking the top edge versus that right edge. So I need to start actually checking everything. So the way I'm going to do that is I'm going to go back to the Polygon object. Right? This is only where I checked this. I only checked 0 against 1. So what I actually want to do is write a loop that goes through all of the edges And let me give myself a little bit more space here. Still not standing in front of it. Okay, go through all of the edges, and I'm going to do this. This dot 0, find edges, this dot I. Now here's the thing. I don't want to do this if 0 equals I. As long as 0 does not equal I, again, I'm only doing this for 0, so this is a little bit silly because I could just make that 1, but I'm just sort of figuring this out. Then find all the other edges. Okay, let's see. Hey, look at that. 0 found this one and this one. So this is working so far. I feel excited about this. Okay, now what do I need to do? I need to then not have 0, but I actually need 2 loops. I'm going to go through j. Every edge needs to check every other edge, and as long as I is not equal to j, then check I against every edge j. So this now should go through and check everything. Okay. Oh, look at this. That's got to be j. Thank you. That's a big problem. Always with the I and the j. Okay, here we go. There we go. This is looking really promising. Look at that. So those points, it's found all the right points. Where's this? In the show function, I got a lot of extra stuff for debugging. So I can kind of get rid of that debugging stuff. And I actually just want to draw to this dot end. So now we should see this. So it got that star pattern inside the square. Wow, that's really exciting. Now, there's one thing I don't like that I did that I kind of want to correct. And then we're going to change the variables and do some tiling. One thing is that when I calculate that vector v, which I think I do in edge here, I think these should really be normalized because there's no reason, it's just things are going to maybe work better if these have a unit length of 1. Actually, this is going to work exactly the same, but somehow I feel like I should normalize those vectors. Normalizing a vector takes a vector and makes it of length 1. Okay, so this is good. Now, let's add the delta. So if you recall, all of this was based on, where's the paper? All of this was based on this paper here. And right now my midpoints are always exactly at the center. But what if I'm going to get some interesting possibilities if I offset from them from the center. So let's see if I can add that really quickly. Nothing is quick apparently, but I'm going to make a global variable called delta, and I'm going to set that equal to like 10, just to see. So where do I calculate those midpoints? In edge, perhaps? Midpoint here. So the difference is the Hankins now don't actually start at the midpoint. And you know what this would be? Let's normalize them here. And what I'm going to do, and actually what I'm going to do is, I'm going to do something a little bit weird. I'm going to set their magnitude to delta. Maybe I should explain what I'm doing now in a diagram. So if you recall, hello. If you recall, if this is my edge, what I first did is I calculated a vector that went from here to here. Then I'm normalizing it and rotating it to start that Hankin. But what I want to do is actually move the midpoint off this way by a certain amount. I already have this vector as a unit vector. If I scale it up by 10 pixels, I could just offset the midpoints in both directions. So let's see now. What I'm going to do is set their magnitudes. Then I'm going to say offset 1 equals p5 vector add mid and v1. And then I'm going to say offset 2 equals mid v2. So I'm just going to offset each of those in one direction. And then, I can go back and normalize those vectors and rotate them. There's a lot of unnecessary steps in here and a lot of extra vectors, but I'm just trying to work it out. Okay, so now the midpoint I should start with offset 1 and offset 2 instead. Simple as that. I should have the delta in there now. So guess what? I sent them in the wrong direction. See how this one went up that way, and this one went this way? They should go in the other direction. So interestingly enough, what I want to do is for offset 1, I actually want to add v2, and for offset 2, I want to add v1. And there we go. So now we can see that delta is there. Wow, this is great. Let's make some sliders so I can change the angles in the delta to see if everything's good. So what I want to do now is I'm going to just go to the main program, and I'm going to say delta slider and angle slider, and I want to say delta slider equals create slider. Let's give it a range between 0 and 25, and let's start at 0. And let's make, and these are P5 DOM functions for quick and easy ways to make sliders. And angle slider, we'll make a slider that goes between 0 and 90 degrees, just for simplicity right now. And we'll start at 60, which is sort of a value that I started with. And then, now here's the tricky thing. I'm doing this just once, but we're going to have to recompute all the Hankin stuff whenever I change delta and angle. So let's just add a draw function and see what happens here. It's still working. Now, I can do this. I can change these sliders, but what I want to do is I want to say angle equals angle slider dot value, and I've lost my train of thought. Angle and delta equals, I've lost my choo-choo coding train of thought. Where's my train whistle? I can't find it. Equals delta slider dot value. Okay. I think I'm converting it to radians. So this is working, right? I'm changing the delta. It broke when the delta got to 0. So I have to investigate that. And the angle is changing. So this is working. Why should it break when delta gets to 0? Oh, it shouldn't break when delta gets to 0 because that should just be what I started with. But it is breaking. So what I can do is I can say as long as, so only if delta is greater than 0 should I bother doing this offset stuff. Otherwise, so I have to kind of, I'm just going to say offset 1 equals mid, offset 2 equals mid. So I just say, there's I'm sure a much nicer, more efficient way to write this. I will think about that later. And then, right, so I'm creating those offset variables, and they're just the exact midpoint. And then only if delta is greater than 0 do I bother to actually offset them. So now I should be able to slide the delta down to 0. No problem. I can change these. Look at this. So now here we go. We are going to do something a little bit more exciting. I just have the whole point of this, right? If I go back to this paper, is that I want to create tiling patterns and tile them and then get all this stuff going inside of the tile. So I'm not going to go crazy with this, but I'm at least going to tile a whole bunch of rectangles. So let's go back. And now it's easy. Now that we've got this working, remember I did this with just one polygon. So I'm going to change this now to var polys is an array. And I'm going to say for var x equals 0, x is less than width, x plus equals, and let's do an incrementation value. Let's say 50. Let's say 100 for right now. X plus equals increment. I'm going to make a nested loop to make a grid of rectangles. Y is less than height, y plus increment. Then I'm going to say var poly equals a new polygon, and I'm going to add x, y, x plus increment, y, x plus increment. So I'm now doing all the vertices, y plus increment, and then x and y plus increment. So this should do poly close and then polys dot push poly. Now, in here then, all I need to do is say for var I equals 0, I is less than polys dot length. One of these days I'll use a for each loop. And now I'm going to say polys, I'm going to do this, I'm going to recalculate the Hankins for every single one and call show for every single one. Let's see if I got this. Line 39. What's missing here? What's missing? I'm missing a close bracket here probably. Yep, I never closed setup. So now we can see I now have my grid. Ooh, some weird stuff just happened there. So this is now completing, essentially, with possibly some minor bugs I will fix, you'll find. Maybe I'll do a follow-up video if it's something really major. But usually it's just an edge case where if it's too far apart or something like that. But what's missing from this are two things. One is a different tiling pattern than just this grid of rectangles. So what happens, for example, if I do heptagonal tiling? So we can see these. What happens if I actually try to create a tiling pattern like this and then fill it with those stars? Or even just something like this and fill it with the stars. If you look at the paper, it will have many examples of different tiling patterns. Can you create this tiling pattern or this tiling pattern and then iterate and create all of the Hankins inside of it? It's showing you different angles, different tiling patterns. And so ultimately, it probably would make sense to come back and do another video with some of these tiling patterns, but I'm hoping that some of you might be able to contribute some of these tiling patterns to the GitHub repository. So that's number one. The other thing is, what I've done here is I've just calculated all the points, but I need to also put those into some form of list so I can draw them using begin shape and end shape so that those could be filled with color. Because I think there are probably some beautiful ways that you could then color all of the different aspects of this. I'm back. Guess what? That was actually, there's a little bug there that the chat helped me fix. Me, I am so me, once again, from the chat, helped me fix this one. So there is a bit of a property here that, that's important to consider, which is that if I'm going to have find that intersection points, they're always going to be equidistant from those edge points, even if I'm moving with delta or whatever. So one thing I can do to double check that I'm really finding the right point is make sure that these two line segments are of the same length. So if I look back at what I was doing earlier, what we just made is you can see there are these glitchy parts. See these glitchy parts? It's finding some weird nonsensical points because it minimized the distance in a way that's not exactly right. So what I could do here is I have this distance, D1 and D2. So I just want to check if those are equal. And I could just say, as long as they're equal, and that would maybe work, but with floating point math, you're often not going to get two values being exactly equal. So really what I can do here is just look at the difference as the absolute value of D1 minus D2. And I'm just not even going to bother with any of this stuff if the difference is not less than 0.1 or something. That means they're equal. So what this should do is don't even bother going through. And again, I could probably make all these sort of nested if statements a bit nicer at some point. But I'm just going to not bother. It's not a valid endpoint if those aren't equidistant. So now if I hit refresh and I play around with this and change the values, I can't break it anymore, and we should be ready to move on to the more interesting tiling and coloring part. So I hope you join with me. I hope you I don't know what I hope. I hope that people are nice to each other and kind to each other and welcoming and tolerant of each other. And I hope that you consider contributing to this GitHub repository with a suggestion, with a pull request, and make some beautiful tiling patterns and share them with me in the comments on Twitter @Schiffman. And also, if you find a particular tiling pattern from history that you're aware of or you know about that I don't know about, tweet me a picture of it. I'm always inspired and enjoying sharing. So, sharing tiling patterns. So, okay, I'll see you soon in a future video, perhaps. Goodbye. Wait, I'm back. I totally forgot something really important here. The whole point of this is to get rid of the grid. This is a never-ending video challenge. The whole point of this is to get rid of the grid, which I could do very easily right now by in the Polygon show function, in the edge show function. Right? I could just comment this out. So now I am only drawing the star patterns. This was the whole point of doing this in the first place, but what I also might do just to have a subtle reference to the grid, if I ever needed to, is just give it some nice alpha, and you can kind of see it there. 50 alpha sort of subtly in the background. So this, by the way, is an important aspect to consider as you start to make your own creative takes on it. And for debugging and giving options, you want to see the grid, not see the grid. And I am sure, not sure, but I would not be surprised if there are bugs are going to be revealed, that things I didn't do correctly if you expand to a more complex tiling pattern. So I hope we can discover those things together, and I will definitely, if there's a significant issue with this, come back and follow up in a future video, and I'm sure I'll hear from you in the comments. Okay, I'm really, really leaving this time. Goodbye.